Welcome to Energy System Modeling first lecture. So today, let's see what we have in store. The lecture one content is going to be on energy system definition. So we're going to go through some examples of energy systems and things associated with them. And then we're going to go through the so-called energy trilemma. Why are we focusing on so much solar and wind? Some tools for you for the energy system analysis. So we're going to go through the basic time series and load duration curves, but we're going to add in some probability density analysis and some Fourier spectral analysis. Something on CapEx and OpEx, capital expenditure and operational expenditure in energy production. And maybe a little bridge towards the second lecture. So energy system modeling, why do we do that? But at first, the energy system definition, what kind of components does it include? So this is a really crude division of these systems, but basically all the energy systems have similar kind of structure. So it has some kind of an energy source. Then you have some kind of a conversion system. So this is kind of like the primary versus the secondary energy that goes into the consumption via transmission. The transmissions in most cases with small energy systems, they're not in a way modeled, but for example, in larger energy systems, such as electricity grid, you have to take it into account. But for example, with heat, if you're modeling district heating systems, that's a really essential part, the transmission. It's a really essential part of the modeling. Then you have the energy storages, the possible energy storages, and they are really a timely topic in this energy system modeling. At least, for example, the heat storages, making the sectoral integration happen. Cheap electricity you can store in the form of heat, and you can also store electricity in a sense as heat if you can extract it from the heat with these thermal processes, circular processes. So the primary energy sources that you're familiar with are the fossil ones, oil, coal, natural gas. Those are the most dominant energy sources in the world at the moment, accounting for approximately 80% of the primary energy. Then you have the nuclear energy and the renewable ones, solar, wind, and biomass. From biomass, you can't really say that it's in a similar way CO2 neutral as solar and wind. Whenever you're burning biomass, you're emitting CO2, even though it's been sequestered in the growing plants. You're still emitting CO2 when you're burning it. So the conversion processes, refineries, thermal conversion, nuclear plants, bioconversion. So for solar and wind, they don't need to have such conversion plants or facilities. Of course, for solar, you have to be able to transform the DC to AC. So that's one kind of a conversion system, but it doesn't require such a plant as shown in here. Then there's the transportation, distribution, so the transmission of electricity or, for example, the fuels. So whenever you have from country to country electricity transfer, that can be dealt with electricity grid. But if you have local heat consumption, that has to be dealt within the city. And finally, energy consumption, transportation, industrial, commercial, and residential.
So we'll be talking more about this modeling of this energy consumption later on. So first you need to define the scope that the energy system involves, defining the boundaries, components that will be included in the analysis or a model. And it can be as simple a system as a household. And that's something that you are most likely going to be familiar with in the coming years if you're buying your own house. So first you have to identify the elements and activities. So you have the energy source. In this case, it's solar. Of course, there's the electricity grid. So you can get electricity out there. But if you are talking about this self-sustaining systems, then you have solar or wind. Then you have the conversion. So there are the solar panels. The transmission could be associated to these components, so these smart meters and the charging station related to this electric vehicle could be classified as the transmission systems, of course, the wire within the house. And then you have storage, but this is also something that can be classified as consumption. So that's why there's the orange and red color as well. And there you have the actual storage, you have a battery, and that's being offered nowadays to household customers in Finland. You can get up to, what is it, like a 100 kilowatt battery for your household. And of course, the company that's providing it is going to be using that for the reserve markets in the electricity market. But you get the benefit of having a battery at your house, and you don't have to take care of it by yourself. So it's kind of leasing it. So they're making money, and you're having more energy security, and you don't have to pay for the highest electricity prices because you have your own battery. And then there's the consumption from different items. That's actually kind of energy production as well, if you have the heat pump in there. So that's not consumption only. So maybe I should add some other coloring there. So define the site, organizational limits, geographical locational boundaries, organizational boundaries. That's something that you have to do. And usually it's rather straightforward in the small energy systems, but when you're moving on the larger ones, it's not as straightforward anymore. You have to develop a scope and boundaries statement, purpose and objectives, inclusion and exclusion. So, for example, what's the main purpose of analyzing this energy system? For a household, it's usually I want to pay less for my energy. So I want to arrange this system in a way that my electricity bill is going to be smaller, my energy consumption is going to be smaller. So there are different strategies like peak shaving and load shifting that you can do even at a household level. And that's what this so if you're in the electricity, if you're buying your electricity with a contract that gives you the market price, then of course you're going to start looking at, I'm not going to be consuming electricity at this hour because it's more expensive. I'd rather shift the load to another hour. Or this way of saving electricity, turning down the thermostat. So we have less energy losses in the system. So then you want to define the period over which the analysis or the model will be conducted. So the time frame, usually we're talking about 1 year. That's the cycle in the energy systems. Of course, you can have a smaller or a longer cycle. Another example of a energy system where you have the same components, you have the source, you have the conversion, transmission, storage, and consumption. And even though you wouldn't have storage per se in a district heating system, the entire system acts as a storage of itself because it has a lot of thermal inertia. you have a lot of water in pipelines. So this is from Kangasala, and this is what Juhani Kotilainen made in or analyzed in his master's thesis rather, and now he's continuing this same analysis in his PhD. So he's trying to come up or analyze different ways of making the system more sustainable and the production cheaper. So that's usually what we're trying to do. On top of that, there's the energy security that you want to increase. I'm still checking if my mic is working. Yeah, seems to be. So there's the peak load, intermediate load plants, base load plants, and you can see that the consumers are scattered around in here, but there are still rather large gaps in between here. So this energy system, this Kangasala district heating system, if I recall right, they had two separate systems that were combined, and now it's a really long kind of a district heating network. So it's really interesting to analyze. If you want, you can read Juhani's master's thesis already in Verbo, and he's finishing his first article now as we speak. So that's an example of this kind of a localized energy system. And the localized energy system compared to this electricity system or the electricity grid that you are trying to model with the spine opt. This is a bit more straightforward of an analysis because you don't have to pay too much attention what the neighbors are doing. One aspect that you usually have to take into account is the electricity price, but that comes in the form of a vector. You have the electricity price and you insert that into the model. That's it. You don't have to make any assumptions that we are going to change the electricity price. Then there's the largest energy system that you are going to be analyzing during this course. So the Finland as an energy system. So we have one price area in Finland, for example, in Sweden with the 4 price areas. And we are interconnected to other countries now, to Estonia with only one cable. And hopefully they don't manage to cut the sea cable between, actually there's 2 cables going from here to Sweden. I think the other one was somewhere around 800 megawatts and the other one was 572. Maybe you can check that from the internet. But there's some 1,400 megawatts transmission lines going from the southern Finland towards Stockholm. So we have a really strong connection in Sweden. A lot of transmission lines to Sweden, Estonia, some to Norway. We used to have lines to Russia, but there's no business being done with Russia anymore. And then there's the internal grid. So in the model, you can say this area acts as a whole, acts as one unit, but then there is, of course, the transmission lines within the country. And for example, in Sweden, there's a bottleneck between the southern and the northern energy areas in there. So you have to make more price areas for the country. So in some cases, the transmission lines are the bottlenecks. So you have to divide the system into different areas. And when you're doing this scale or energy system modeling on this scale, then the resolution, of course, is going to be lower. So we don't take into account every thermodynamic detail of certain production assets. It's mostly done with this kind of linear assumptions. So let's bring the example to kind of a bit more concrete level. This is something that I found from NATO pages.
So they have this military energy production is usually something that they want to do kind of it's off grid, so you don't have any support from the electricity grid, and then you have to analyze if the certain assets that you have make enough energy for the consumption at all times. So in that particular case, which seems that I haven't got the source in here, I'm going to add that later. So what they had is small scale wind and solar. I think that was somewhere around in the 10 kilowatts range that they were producing. And I made a consumption up for it. So in this case, I didn't make any. I have a model in Excel, and I made up consumption. So that's made up of two, I think, beta distributions that I will use in there. So that's a rather kind of reasonable consumption profile. So you have less consumption during the nighttime, you have something in the morning, and something in the afternoon hours. Maybe this is not a representative of this kind of a military system, but we'll look at that. Then there's the conversion, so some kind of an inverter that can feed power to the consumption and the wind power. You have a storage system that can store both this solar and the wind turbine. And then you want to have a backup power. So you have two diesel generators. So that was their solution to this energy system. And whenever you have an isolated energy system, it's better to have more energy production forms and something that you can dispatch at will. So that's this increases, these diesel generators increase the energy reliability. These increase the energy sustainability. And of course, then you have the price that's really high if you have all these kinds of components. So I made a really kind of simplistic analysis on this in Excel. We're going to go through that later on in the course in the exercises. So what I have in there is I have the consumption plotted against the production from the solar and the wind, and I scaled it in a way that the consumption at some points is higher and at some points it's lower, and that's rather typical. And even at a country scale in Finland, now we have such a high amount of wind energy that's what's happening in a larger scale as well. So what happens is in here is you have this solar and wind power, and you can see I made some Gaussian distribution and I added some random noise into it. So that's really not making it making actual production modeling, but rather I just made a profile for it. And the wind, I got some wind data from a random location, and I calculated the wind production based on that. So these are really typical profiles. The sun shines during the day, and the wind kind of supports it in a way that mostly during the winter time, there's less solar, but usually there's more wind power. Maybe there might be some other reasons as well for that. But for example, in Finland, when you have small or the rather cold air during the winter time, then the density is higher, and that's why they produce more electricity. So if you look at the production volume of wind power, you can see that it's slightly higher during the winter time. So also in this, how do you say it in English, diurnal analysis, you can see that solar peaks during the day and the wind, in this case, peaks during the night. So then you have the energy storage, and what I was doing in the analysis itself. Let's see if I can open it from here. So what I was doing in the analysis itself is I wanted to see how big of a energy storage would I have to cover these gaps in here. So if I put the energy storage into 0, you can see that there's the consumption and the production, and there are gaps in between. So we would have some energy in here that we could utilize. So if I increase the storage, if I increase the storage capacity and say that there's the same amount of energy, so the energy storage is full, or if I start increasing it, you can see that I can utilize the solar energy from here to load up the batteries, to charge up the batteries, and then I can utilize it later on. So I can shift the curtailed power. This curtailment means that we would have to cut it off. We can shift that to another time in here if we have a larger storage. And there's still a gap in here. And of course, if I have this random factor here, you can see that there are some changes in the wind production, and there are some changes in the solar production. Of course, I could make some noise and variation in the consumption. That stays now constant. But in this way, I can analyze different scenarios, and I can see how much I would have use for the diesel generators. So how big of an energy storage I would have to have, and how much energy I would have to have initially in there to minimize the diesel generators. And there you can see how the storage behaves. So in here, I have a certain amount of energy in the store. Then I have a surplus of production. So I charge up the battery, and then I start discharging it because I have a gap in between the consumption and the production. So that's a really simplistic analysis of a small-scale energy system, but you can still make it a really interesting one. And in here, you can see that there are certain aspects that I have to take into account. I have to take into account production modeling. I have to take into account the consumption profile, and then I have the energy store. So that's really a simple system. And the energy storage, I can model that if in the previous hour I have a surplus of energy in here, then on the next hour I have, of course, that depends on how much charging capacity or charging power you have in the battery. But that's available later on to be used in the model. Yeah.
What do you mean by the random factor?
What do you mean? Oh, the random factor. I just wanted to have how that manifests in here. I have a random number that I scale the, or rather, I subtract from the Gaussian distribution. So the solar production is a Gaussian distribution because I thought that the solar goes up and the sun goes up and the sun goes down. If there were no clouds, no obstructions between the sun rays, then you would have a really smooth profile. But now I want to make the effect of this cloud covering. So it's not always the same. There can be different kinds of days. So that's why I can have a random factor in here. So that's a way of making this noise into the system. So you can see, are there days in which, if I increase the random factor in here, are there days that the solar is not going to be enough, or so forth. So that's kind of making this different kinds of scenarios. So then about the energy trilemma. So the energy system that you saw in the example, or at a household or at a country scale, what we want to analyze it for is it affordable? Is it reliable? And is it sustainable? So that's the kind of three things, and you can choose usually two out of those, or you can balance out that you can make it less affordable, but a bit more sustainable. So you can have some aspects out of these all, or then you can just choose two and ignore the first one or the third one rather. So sustainability focuses on reducing environmental impact. So our main bad guy at the moment is CO2. When I was younger, it was the CFC, chlorofluorocarbons. That wasn't really associated so much to the energy production per se, but there were technologies that were emitting these CFC gases and destroying the ozone layer. And to some extent, I think that problem is now solved. So we have addressed that problem. And at the moment, we are addressing the carbon dioxide problem. So sustainability focuses on reducing the environmental impact, promoting renewable energy, because they have less of an effect to the overall environment. Challenges: transitioning to clean energy while maintaining cost effectiveness and stability. So cost effectiveness, the stability, they are at least were before rather hard to maintain. And that's why, for example, Finland was paying these subsidies to wind power before 2017, or actually it's paying still for the amount of wind production that got into that system. So subsidies were the way to kind of increase the amount of wind. But now it's like operating on its own without subsidies. So reliability ensures a stable, uninterrupted energy supply to meet demand under all conditions. And that means that you have to have this kind of dispatchable, really dispatchable energy production, like the diesel generators. It seems that the sun is not shining, let's crank up the diesel generators. So that's reliability. Challenges: maintaining grid stability with intermittent renewable and preventing disruptions from natural or human-made events. Natural or human-made events, referring to what's happening in the Baltic Sea, cutting off the cables, cutting off communication lines. So that's really something that the Finnish people at the moment are taking notice. We have to do something about it. Affordability aims to provide energy at a cost accessible to consumers. So that's a really important thing. What the consumers had to endure during the energy crisis 2021, 2022 were really soaring electricity prices, and I also had to pay the price for that. So that's something that we don't want. We had a lot of renewable energy production, even at that time, but then the global energy crisis, that was partially at least due to the fact that after Corona, when the industrial system were kind of like cranking up, starting again, then and there were some local energy shortages all over the world that reflected in higher fossil fuel prices, and that also showed in our energy system as well. So sustainable, reliable, affordable. So if we choose from these technologies, we have only renewable energy, or then we have renewable energy with this dispatchable power. Then we have renewable energy and energy storages, and then we have it all. We could say that the first system is affordable, it's sustainable, but it's not reliable, because there's going to be a lot of energy shortages. So you have power when you have power, and that's it. The one where you have the diesel generators, it's reliable, it's less affordable, but it's definitely not sustainable. And the next one, maybe this is a balance of affordable and reliable. You increase the reliability here. Of course, that depends on the energy storage size. But usually I would say it's easier to acquire these diesel generators rather than just these
large enough energy storages. And then the final one, we have a reliable system. It's might not be too sustainable, depending on how much we have to use the diesel generators, and it's certainly not affordable. So you have to define what you want. In military applications, of course, reliability is king, so that's why, and maybe the affordability is not. So it depends on what you want. So some ideas. What aspects of the energy trilemma rather does the Finnish energy system fulfill, in your opinion? Ideas, please.
Reliability.
Reliability. Yeah, that's something that we pretty much take for granted here. But when was the last electricity? What's it? When the power went off. When was the last time? Maybe once during the summer, but the electricity came right back on. So we have a rather reliable system. What else? What other ideas? Please.
I think it would be some kind of equal measure of the distribution of all three. Kind of it's also sustainability. Well, electricity is still quite affordable in Finland.
Yeah. Yeah, so it's a rather good balance of these three. We have somewhat affordable energy prices, at least now. A couple of years ago, not so much for the consumers at least. We have a rather reliable system. Of course, we have the threat now of some monkey business happening in the Baltic Sea. And then the sustainability aspect. Is it 90% of our electricity is produced with CO2 neutral sources? So we have a lot of wind power, we have a lot of nuclear power, and we have a lot of biomass combustion. But of course, CO2 emissions are not the only thing. So if you're talking about nuclear waste, how to dispose of that, well, Finland is taking care of that as the first country pretty much in the world. And again, the question that is biomass when you use it for combustion plants, is that actually carbon neutral? But based on European Union legislation, it is. So in that sense, we have a really, especially electricity system, we have a really sustainable electricity production. So we're kind of striking a rather good balance of all of those three. Any other ideas on that in Zoom? Do you have some ideas in the chat or something you want to say? But that's something you have to kind of predetermine what you want out of the electricity or the energy system, rather. This is in Finnish, unfortunately, but I can translate to some extent. So this article talks about the reliability being a key aspect in this green transition. So that's something that's being demanded in here. For the consumers, the price is the most important thing. So, of course, I pay thousands of euros of electricity bill in a year because I live in this is called detached house. And you have to pay for the energy and you have to pay for the transmission. So a couple of thousand euros, a bit more than that. So I would say for me as a consumer, price and reliability are the most important things. In here, it's kind of like price, reliability, and climate. They all interest the consumers. And the other statement is here that in the Finnish parliament, there are only parties that are in favor of nuclear power. So we are a rather nuclear power positive country compared to, for example, Germany that shut off all of their nuclear power plants. So they don't have as much of that dispatchable base load anymore. So you can understand from here what that does to the energy reliability or sustainability. So there are these kinds of ripple effects that start from, for example, Fukushima nuclear catastrophe, or what happened in the United States in terms of this fracking technology. So when this shale gas, they were able to produce that in fracking, so that increased the amount of natural gas used in the United States, and decreased the amount of coal. So coal market price plummeted in the early 2010s, and that's why, for example, in Finland, they were using more coal during that time. The four horsemen of the energy chain. You have primary energy, you have the secondary energy, final energy, and useful energy. So raw, unprocessed inputs into the energy system, then primary energy converted into transportable form. So you can transport, for example, oil or electricity or heat via district heating network. You have the secondary energy that is delivered to the customer. In the district heating system, something is delivered also to the front. And then from there on, you have the useful energy. So you have losses, and losses. The more complex of an energy system you have, the more losses you have, the more possibilities of losses you have. So examples: coal, wood, oil, electricity from power plant, charcoal from charcoal kiln, and gasoline from oil refinery. Electricity delivered to home, charcoal sold at the market, and gasoline at a fuel pump. We have light bulbs in here, glowing, giving us the light. Then you can burn charcoal in a grill, and you have these hydrocarbon fuels in liquid forms that you can utilize to move your vehicle. And I always said that these hydrocarbon fuels, I mean, we're not in hydrogen economy, we're in fossil or oil economy. And it's really easy. You have like 10 liters, a bucket full of these oil refinery products that you can pour in your car via the pistol, and it takes 1 minute. And then you can move your car to Helsinki and back and a couple of times. It's really simple and easy. So that's why we're facing a lot of problems with electrifying the vehicles or finding a substitute from these biorefinery products. The current system is really optimized in terms of this reliability and maybe even cost. So primary energy available as resources, fuels burned in power plants before it has been transformed. So that's why we don't have energy production, we have energy conversion. Includes the energy to the end user needs, and some of it is lost when it's transformed into usable form. And the substitution method, I wanted to take that in here for your knowledge. So you have a link in here so you can see what the substitution method means. So in here, for example, you can say if you use 1 unit of, or rather 3 units of coal, you get 1 unit of electricity. But the substitution method means that when you have non-fossil electricity generation, so
for example, wind or solar. It means that in these charts that I'm showing you, they are processed with this substitution method. So they are assuming that the equivalent of this thermal power efficiency that's being increasing or increased in these calculations, they're using that to calculate the amount of wind or solar power. So you don't have just one unit of solar power. You have one unit divided with this 41. So you have more solar power, because otherwise the comparison wouldn't be fair. If you have 1 unit of, or 3 units of coal power, you lose a lot of it, but you don't lose similar way from this solar and wind power. So that's why in these statistics, they are using this substitution method. And in here, you can see Statistical Review of World Energy 2024, other renewables, no, it wasn't said in here, measured in terms of primary energy using the substitution method. So this isn't the actual amount of solar that's being produced. Rather, when you compare it to fossil fuels, you use the substitution method and increase the amount. So in Finland, other renewables, it didn't start from here, but it wasn't put into the statistics in a similar manner before this 1990. But what has happened with us is that the coal power is declining. Gas power has rapidly been declining because we have been pretty much 100% reliant on Russian natural gas. Oil, it's really hard to get rid of because we have the vehicles running on oil. Nuclear, you can see Olkiluoto 3, Olkiluoto 3 in here. Hydropower, it has this variability in it based on what kind of water situation we have, how much rain, how much floods, so forth. Biofuels, they have been on the rise, especially in the district heating systems. They have been replacing a lot of fossil fuel with these biofuels. And solar is peaking up, but it's nowhere near the scale as the other ones. But the most dramatic change has been in the wind power by far. No other energy production form has risen at this kind of a rapid rate. And that has been making the energy system analysis rather interesting, since you have a lot of this variability in there. And then you have to make these production scenarios. What if we build more? What if we build even more? What if we build even more and we don't have consumption for it? What do we, where do we get the consumption from? Is it hydrogen production? Is it metals production? So forth. So that's the scenario creation. So why do we focus on solar and wind? It's because of this one. The area of the circles represents reasonably assured recoverable energy reserves from both finite and renewable resources over the next 30 years. Solar and wind are, well, solar is off the chart and wind is the second largest. So there's a lot of solar and wind to be harvested. But of course, we need the system for that. And we need the energy storages for that, because that's variable production. This doesn't say, this says the amount, this doesn't say the characteristics of these energy forms. But yeah, that's why we're focusing on solar and wind. And in Finnish energy system, you have nuclear. This was in the summer when the Olkiluoto 3 turbine tripped in here. The electricity price was otherwise high, and they had to use a lot of these natural gas turbines to cover up some of the lost power from here. But you can see the production and consumption. There's the production and consumption. So sometimes production is higher than consumption. sometimes consumption is higher than production. So import, export, that's what we have to do. But you see problem. Wind is going up and down, up and down. And you can see usually when there's a lot of wind in the system, that the price is low. But when the wind power goes down, the price goes up. So it's that kind of a dance. And that's why you can have these companies selling you these batteries for household use. So that's the Finnish energy system at the moment. We are somewhat in a turmoil. What ways can we make this system better? So electricity from fossil fuels versus wind and solar, you don't have so many losses in there. So we can decrease the amount of loss, but then you increase the variability of the system. So compared to gas heating, you can use heat pumps. So from ambient heat, you can extract the heat. And again, you don't have to use so much primary energy. So that's why heat pump is a really good system. But it's more, or rather less affordable. So it makes the system less affordable. And there are more moving parts again. Transport, this has been a really hard, tough nut to crack. So electric mobility, I would advise you to watch this Mark Mills energy transition delusion from YouTube. It has a really good idea on this, what's going to happen to the metals. We're talking about peak oil rather, or peak coal, but we are not talking about peak metals. So where can we find enough material, or can the mining industry produce enough material for the green transition? So the variability in wind production, that's something that we have to take into account also in the energy system notes, and then local wind production versus the capacity factor. So production versus capacity, production divided with capacity. In Pori region, you can see there are a bit more steep changes. If you're talking about the overall the production in Finland, it has still a lot of variability that goes hand in hand with Pori's production, but maybe there are a bit less or steeper, less changes. Actually, a lot of our production is in the western coastline, so that's why these go really well hand in hand. But that's something you have to take into account. So can you extrapolate from the localized data to the overall data? If you want to take the wind production in Finland, or if you want to model it based on how windy it is, you have to have different locations to get the wind speed from. So how much time do we have? Half an hour. That's good. So we can go through the toolbox for the energy system analysis. And that's something that we're going to go through in the exercises as well. So this is kind of a prelude for that. So time series analysis, load duration curves, those you are most likely familiar with. Then you have the probability density. That's something that we haven't covered in my courses, at least before, and the Fourier spectral analysis. This data aggregation is a tool for the box, but we're not going to go through it here rather than later on in the course. Time series analysis. So in energy systems, it represents the sequential data points, electricity demand, generation, price, measured at regular intervals, or not at so regular intervals in some cases, especially now when our electricity systems is shifting towards this 15-minute interval rather than 1 hour interval. And in some time series, you can see that there's 1 hour, 1 hour, 1 hour as the interval, and then you see it switches up to 15 minutes. It's a bit of a hassle. You have to modify the data. Purpose captures the variability in patterns, generation over time or consumption over time, identifies trends, seasonality, anomalies,
if you have some anomalies, they can show up in this time series, as I showed in previous slide related to this turbine trick phenomenon on the green. Nuclear power went down. That wouldn't show in a non-duration curve. So applications, modeling intermittent renewable sources to assess variability and predict output. So you can, for example, calculate the variability, standard deviation. Forecasting energy demand and planning grid infrastructure and simulating the integration of storage systems, demand side management. So there is a certain household that I have an easy access to the data from Elenia Island. So that's a detached house with, how do you say it? You have an electricity boiler, but you also have heat pumps in there. So that's time series and the long duration curve of that system. So you can see during the summertime, you have less consumption than in the winter time, because during the winter it's cold, and in this certain household, the electricity is being used to heat up the house via the boiler and via the heat pumps. And there's a huge variability. You can see that in the daily profile. Goes up, goes down, goes up, goes down. But of course, there's the temperature. So that kind of evens out. In the nighttime, it's colder, so the heating electricity consumption goes up, and during the day, it goes down. So, long duration curve. Long duration curve is a graphical representation that orders the demand levels from highest to lowest in a specific period. You have to have a specific period, and then you just say there's the largest, the second largest, and so forth. So in the frequency distribution of demand. So summarizes the operational requirements for the energy system. What is the maximum, what is the minimum, and what is in between? So how much do you need? Base load, intermediate load, and peak load. Helps in understanding those. So arrange time series, demand in descending order, and plot against time. Designing sizing power plants, storage, transmission systems, evaluating capacity factors and full load hours. So how many hours would you have to produce or consume the energy in a way to so you would meet the energy demand or production versus the highest load production. So there's Finnish electricity production, or rather consumption. So there's the time series and load duration curve. And that's something that you have gone through before. And if I'll show it quickly in Excel, let's see, from here, I'm going to have a certain amount of hours from here. Let's put it to somewhere around 100, like this. And then I'm going to take random numbers. So I'm just going to put rand and have these generate these random numbers. And then I'm going to say large. So if you want to make this in Excel, this is how you do it. And in here, I'm going to put dollar bills. And I'm going to say this is the first, or the largest rather. And now I have load duration curve and time series that I can draw as a function of my time unit, which is this 1, 2, and 3, and so forth. So you can see the variability in there, and then you can see them in descending order. And to make it a bit more interesting, I can put, for example, this to the power of 3. So we'll see a bit more, rather this one equals to the power of 3, just for the sake of example, so it doesn't look as boring as that. So let's move it there. And now we have the bit more parabolic exponential decay type of deal. So what else? Probability density. So this analysis involves estimating the likelihood of different events.
occurring within the time series data, quantifies variability and uncertainty in these parameters, and provides statistical basis for stochastic modeling and risk assessment. You can use these histograms or kernel density estimation that we're going to try and do in the exercises. Kernel density estimation, it's something that you can do it in Excel, but in the exercises, we'll try to use AI, for example, ChatGPT, to generate a code for Python to make us this kernel density estimation. So what it means that if you have a number in here, so this represents the amount of numbers that you have in this certain span. And then if you have triangular or Gaussian so-called kernels, so you're starting to add up these functions, either triangular or Gaussian, or there's many other kinds of these kernel functions. But if you start to add them up, they start to form this kind of a distribution, a smooth distribution. You don't have to make this as a histogram. I mean, you could calculate all of these numbers specifically at a certain range, but then be this rectangular. So addressing these uncertainty and reliability of renewable energy outputs, designing a robust energy system capable of handling variability. So I'm going to show you an example. Here you have Finland and you have the household. This is the probability density. This isn't calculated with the kernel density estimation. Rather, I have just said that how many numbers hit in this gap, between this gap. So you can make that in Excel, but if you want this kernel density estimation, maybe better to use Python or MATLAB for that. So in Finland, you can see that there is a peak maybe in 6,000, 7,000 megawatts and another at 10,000 megawatts. So that could represent partially the diurnal, the daily kind of shifting in the power, or then it can also be related to this winter and summer. In the household, you don't see such dramatic difference. So a lot of the power is concentrated on the lowest, the lower range, rather. But there are some that goes up to even 50. So from here, you can see that there's a lot of a need for a large energy system that can operate at a very flexible range. And the most power is concentrated into here. I'll try to show it really in a fast way in Excel. So I had some, actually what we need is here, we're going to take minimum, which is 0, and then we're going to take maximum, which is 1, and then we're going to make steps. We're going to have 20 steps. So from 1 to, we're going to make 20. So this is how many slots I have in here. So steps is going to be 20, and this dx is then going to be the maximum minus minimum divided with steps minus 1. So that's my dx. So if I start from 0 and I always add to the previous one, this one, and keep it as a constant, I have the gaps. So how many of these, I'm using count ifs. So this count ifs calculates that if I have this, it doesn't matter if it's the original data or the load duration curve. So how many fall in between? Let's still move these ones. How many of these values fall in between 1 and 0.52 and so forth? 0 and 0.05. So now if I draw the, so that's actually 0 in here since it's 0, or these ones rather, yeah. So in here I have the density function, and you can see that the peak is in here. most of the power values fall in here. And if I make a correction in here, if I still put to the power of 4, so I'm decreasing the amount of the small numbers, it makes it even sharper in here. And what I can do is I can increase the resolution in here as well. If I increase the amount of steps, so I have 39 steps in here, 39, and then I calculate it throughout from here, and take this one. It makes it a bit sharper. I have a bit more resolution in there. So this kernel density estimation, what I have in Python, let's see if I can run it from here. So this is the kernel, yeah. Let's see if it runs it. This is, by the way, entirely prompted with ChatGPT. So I don't have to use any other kind of coding than just prompting. For some reason, it seems to be rather slow. Let's see if it does. Yeah, no, it does the trick. So there you can see from the Finnish electricity production, the density function. And what we can do is we can increase the bandwidth. So if I increase the bandwidth and do it again, let's see what happens. It should be smoother. So I don't get the exact variability, but I can still recognize the largest patterns that occur in there. So there you have it. So you can decrease or increase the bandwidth and make it a bit more smooth. So that's one analysis tool. And then there's this Fourier spectral analysis. So that's something that you might want to look into as well on top of just these lectures. It gives you a sum of sine and cosine waves. So the purpose is to kind of find the most dominant sin or cos waves from the system. So what that enables you to do. So I can show you the example from here. Actually, in here you can see from wind power. When you get this spectral density as a function of frequency, you get spikes, one spike for 1 year, 4 days, 1 day, and 1 minute. So these spikes relate to macro meteorological range, and there's a certain spectral gap that doesn't contain too many spikes. And then there's the micro meteorological, and that's a hard word to say, meteorological range. And that's because of the turbulence of the air. And this is what happens in an atmospheric level, those larger changes. So what I have in here on the next page is there's the hourly wind power capacity factor in Finland. And now, as you see, we have an hourly distribution. I can't go into the minute scale. I can only estimate it up to 1 hour, and that should be a spike in the system. And if I make this kind of a Fourier analysis, so that's the original data, and I have the Fourier sum, so this has less of time span here. I have Fourier sum of, was it maybe 100 of those most dominant spikes in the spectrum. So in here you can see 2 of them. That's the yearly sine wave. And you can see it from here. There is some funky business in the data here, as you can see. I don't know where that was from, but this was from, or what was the origin of this error in here. But this was from FinGrid. So they provide you the data and the capacity factor. You can calculate based on that. So you can see there's kind of a sine wave depicting the overall yearly behavior. So lower amount of production during the summertime, higher amount of during the wintertime. And then there is the monthly. So there's a certain cycle that goes on monthly in there. So what I can do with, again, Python. So I have this Fourier analysis in here. And again, I haven't coded a single line. I just prompted it. What I asked it to put this frequency analysis, Fourier spectral analysis on this Finnish electricity consumption time series. And you can see that it gathers up this signal, or the sine waves rather, in here. And you can see that there's a weekly change, there's a daily change, and then there's even during the day, it finds that there are 2 spikes in the data. And from here, you can see the sine waves that it's trying to gather up together. So it's finding the frequencies from the data. And that's something that you want to analyze if you want to estimate, for example, an energy storage size. For a solar driven system, you have this diurnal change. Goes up, goes down, goes up, goes down daily. But with wind, it's more like 4 days or a week or so forth. So that's what you get. So you need a bigger energy storage for wind-driven system rather than a solar-driven system. So that's what you can get from it. What else did I have in mind? That's something you can't really do in Excel. So forget Excel at that point. If you want to make this Fourier spectral analysis, then just ditch that. I think it also had another, the spectral. For some reason, there's a really high spectral spike in there. But for example, this spike in here, you can see that it's 0.042 something. So that's the 24-hour, so 1 day spike. So you can see that there's a high spectral density in there. But yeah, we'll try and do this in the exercises to some extent. But Fourier spectral analysis is something that you want to do. And because of this artificial intelligence, you have all the coding languages at your pocket now. So it's not about your technical ability anymore. It's about having a vision. What do you want to do? What do you want to analyze? Why do you want to analyze? So I'm a big proponent of using these AI tools, especially for coding, because it enables you to get from a really zero, well, maybe not from zero level, but really small level to an intermediate coder. And you can make these kinds of program analysis tools really simply. So you have to have a vision. You're more of a philosopher nowadays. What do you want to do? No, rather, why do you want to do it? CapEx and OpEx, that's the kind of like the final thing we're going to cover in here. So this is for the cost analysis. You have to understand where this CapEx and OpEx originates or comes from. CapEx represents the upfront costs required to establish energy production system. One-time investments and components of CapEx, you have the infrastructure and equipment costs. So, for example, power generation equipment, civil works, electrical systems, and so forth. Then you have engineering, procurement, and construction. So somebody's going to be doing it for you. You're going to have to pay a price. When you have a heat pump installed in your house, there's going to be a person who comes in, installs it. So it's not all about the system cost. It's about the engineering, procurement, and construction. Land acquisition and site preparation, and that's really essential in renewable energy, because you have to have land for wind power, for wind turbines, and you have to have a proper site that has a really nice, it has to be windy. And of course, for the solar generation, you still need land as well. You can see 2 megawatt, so peak 2 megawatt
power plant next to Idea Park, if you see the Google map. That's the size or land area that's required in Finland for that. Licensing and permits, contingencies. So there are some uncertainties, unforeseen events, cost overruns. Usually it's cost overruns rather than vice versa. So you have to have a reserve for that. So characteristics of this CapEx: one-time cost, typically depreciated over the asset's lifetime. And that's in the calculations you have to decide depreciation time or running time, 20 years. For nuclear power plants, 60 years. For wind turbine, 20, 25 years. For a heat pump, in my case, with no maintenance, 15 years. I don't know how you withstand that. I don't know how much, but the person who came in and installed the new one said that, yeah, you had a decent amount of this, what's the word, kylmäaine, the salt liquid in there in the system. So it hadn't even leaked out. So 15 years, that's a good time for a heat pump. So OPEX represents the ongoing costs required to operate and maintain an energy production system. And usually in our crude calculations, we only take into account, for example, the fuel price. So the fuel price is the most dominant in most cases, natural gas, nuclear fuel, so forth. But there's also maintenance costs, scheduled maintenance, unscheduled repairs due to wear and tear, as in these nuclear power plants. Staffing and operations. The more you operate it, the more staff you need. In some cases, the staffing is also kind of a fixed cost. Utilities and auxiliary power. Electricity or heat required for internal operations. Cooling water, compressed air, so forth. Consumables, chemicals, lubricants. That's something you have to take into account. Not as high a level as the fuel costs, but still. Regulatory and compliance costs, so monitoring emission, costs for inspections and audits. That has to be taken into account based on what kind of a power system do you have. Insurance and taxes, waste management. So these are recurring costs, affects the operating profit of the energy system and often scales with the production. More fuel usage during higher output. And what you can find from many sources in here: long-term electricity price forecasting, Finland neural network model to demand with demand and production, using neural networks to predict the behavior of the system. Siri Lantala, 2013. So it's a really recent master's thesis, and it's a really good one. So if you want to read master's thesis, there's a good one. So here you can see CapEx, how much does it cost? Fuel price, operation and maintenance. This is the EU based allowance for the CO2 emissions. Startup costs. So if you start a fluid aspect up, it costs a lot more than firing a gas-fired turbine. So the startup costs of that district heating station next to the fire station here, 100 megawatt oil burn. It's a lot less than the startup time for this Quebec boiler in the other corner, so the biomass plant. But biomass is a lot cheaper in general. But you don't want to spike it up and come down. On the oil, you can do that. And levelized cost of electricity or energy. So how much costs you have over lifetime and how much electricity or energy you have produced. And if you know all of these costs, then you can start making biddings for the markets. This isn't exactly what it costs to run, but these are rather these biddings in the markets. And sometimes nuclear power plants, they make negative biddings because they just want to keep the power plant on. So no matter what, we're going to keep it on. But in here you have the order merit order. Solar and wind really cheap. Nuclear, if you have an old power plant that doesn't have too much capex left, then nuclear is the cheapest one. Then you have hydro, CHP industry, or CHP district heating, and then there's the export. And what the wind power does, this is explained in the series work with this kind of a depiction that you have this what's it, accord pipeline. So it just moves back and forth, back and forth. So it sometimes pushes the other production out of the market. So now the price decreases really drastically. There's a lot of links for this OPEX and CAPEX in energy production, so I'm going to provide them with the lecture material. So if you need some values for it, you can check these ones, or you can read the general theory here. So the final aspect, why do we want to make energy system modeling? Because you can't make tests in large energy systems. That's really hard. In smaller energy systems, you can, but in larger ones, you always have to model them. Critical insights and strategies can be derived from those models. It supports decarbonization. It gives an insight. How do these new production assets work in the energy system? It addresses complexity, so we can see how different systems work with one another, how they work in unison. Incorporating temporal and spatial scales, we can increase the resolution to smaller scale, so we can see what happens minute by minute, or then we can calculate what happens yearly in the next coming years. Managing uncertainty. So as you saw in the example, I had this random factor in there. I can run 1,000 simulations with a random factor and see if there's a certain event that occurs that makes my energy system fall. But you don't want to do that in real life. Behavioral and social insights. So provides a more realistic foundation for policies that affect consumer behavior and societal trends. And policy and investment guidance. So these models provide insight how to make decisions. So it's really hard to kind of base those decisions of an energy system into a gut feeling. It's so complex. And nowadays it's becoming more and more complex. You have a lot of these primary energy sources from which the pricing are fluctuating. And then you have the energy conversion storage stages. So heating, electricity grid, natural or gas grid, they are being more and more interconnected. That's sectoral integration. So that's why you have to be able to model all of these systems in unison, or at least you have to have a boundary condition that takes into account what happens in the other system. And then on top of that, it's good to know, based on behavioral changes, based on certain energy scenarios, what's going to happen to transport. You have to take into account legislation. If the legislation pushes the electrification of vehicles, then you're going to have scenarios where a lot of electric vehicles are going to draw power from the network. So you have to have a simulation where all of them are doing that together. So does it fall? Does the spike cause problems? And the same goes with the others. So that's the kind of power of modeling. You can make different scenarios. You have to build a realistic model, and that's hard. But if you manage to do that, then you can simulate all different kinds of scenarios and see this route is the best because. Yeah, so we barely made it in time. So what we covered here was the definition of energy system, something on the primary energy, the substitution method, the toolbox,
and why do we want to do energy system modeling. So tomorrow we're going to start with the calculation exercises. So you don't have to bring your own laptop with you because it's the computer class, but of course, if you want to, you can do so. Yeah, we seem to be running out of time, but if you have any questions, I can answer them still.